Hi there guys, well welcome back. We're about to do 4P and 4Q. There's only actually two example questions which we have to do here. And this is all about drawing the derivative of the function when you're given the original function, and therefore drawing the second derivative from the first derivative and so on. We're also going to think about, in example 33, how we go backwards as well, how we think about drawing a sketch for the original function, seeing whether that's possible or not if we're given the derivative. Okay, so this one says copy this graph. There we go, I've done that one. And sketch the first and second derivatives of the function on the graph itself. Okay, well, that's what we're going to have a go at. So let's have a look at this then. So there's our function. And first of all, we know that when we're getting f dash of x is equal to 0, we definitely know that we have turning points. Okay, well, it's possible, again, that we could just have, total flat line. But we're talking about with polynomials or with functions which aren't just, completely basic, like a horizontal line. When we've got f dash of x is equal to 0, we have turning points. Okay, so at this point here, we have a gradient of 0. At this point here, we have a gradient of 0. At this point here, we have a gradient of 0. So those points are going to plot as zeros. Okay, so we're going to get plots of 0 for each of those turning points. Okay, now on this side of the turning point, we can see we have positive gradient. So it's a positive gradient here, but on this side we have a negative gradient. Okay, so we're definitely going to have zeros here, so those are fixed places. But then we have a positive gradient on this side, and we then have a negative gradient here. So that means we need to plot positive here and plot negative here. Making some sense? We're saying, well, look, the gradient is positive there. So when I put in, I don't know, f dash of minus 10, I should get out a positive answer because, look, it's a positive gradient. We're plotting the gradient at any particular point. Now, here, it's a bigger gradient than here. That's nearly 0, and then we're getting 0. So we're coming down to 0, something like this. Okay, and then on the other side, we can see we've got a negative gradient. We've got a negative gradient all the way to here, and we've got the most negative gradient here. Which means to say that somewhere around here, we have this most negative gradient, which looks, it's difficult to tell from the scale actually, but we have some point down here, and I don't know where that is. Okay, but I'm just sketching this at the moment. So we have some point down here, which is the most negative, and then it becomes less negative, but still negative up until this point here. Okay, now you can probably see how this is going to go. This is going to go like this, this, and something like that. Okay, that's how we're going to finish this one off. But let's make some sense of it. So between here and here, we can see we have a positive gradient, and the most positive is around here. So we're going to have a turning point at the point at which it's most positive. It doesn't necessarily go through that point, but maybe it goes like that instead. But we're going to go like that, and and then the next bit is going to go, we've got a negative gradient between here and here, and it's most negative here. It's going to go somewhere through there. Most negative point here, point of inflection. And at this point of inflection here, we have the most positive. So it's positive between here and here. It's just an increasing function there. So there we go. And then it's negative afterwards. So it's just negative. Going down to sort of evening off, it seems. Looks like it's going to turn again there as well, that function. So it seems to me like we're going to sort of hit something like this. And again, maybe that one sort of turns there slightly at the end as well to hit the maximum negative gradient, but we don't really know. Okay, so there we go. That's what the function should look like. Let's check that with the book. That's what they're drawing in. Now they're only sketching it in here, and in fact you can't really know the scale of this unless you actually work out some of the gradients. So if you work out your gradient at, let's say for example, this point here. So at this point, our maximum gradient. So in other words, find out that point of inflection. Then we can, at that x point, we can then work out what our height is there as well for f dash of x. Okay, so we can work out this height, but we don't know that it's necessarily there. This may be stretched upwards or down. So although we've got our sketch on there, we've only got the shape of it. We don't have the scale, the stretch basically in the y direction. We don't have a y direction scale. Now, possibly we can think, well, this is much more steep than, say, for example, this. So in fact, this point here should be much lower. Okay, so that maybe that's a way of criticizing my graph here, in fact. That should be lower than this point here. And likewise, this gradient, okay, let's do this in the color. Okay, so this gradient here is much steeper than, say, this gradient here. So the maximum positive gradient here should be higher. This one, this curve here should probably be higher like that. Okay, so that's probably a better version of the graph going like this. Okay, let's just do that, something like this purple. So we're getting like this, higher, lower, and lower there. Okay, so something like this. Let's have a look at how they've done it. Yeah, they've done it a bit more like that as well. So maybe I'd lose a mark actually for not indicating that we definitely have a steeper gradient at those points. Okay, well now it says we want to do the second derivative as well. Well, what I'm going to do is take the graph here, so the green graph. Okay, so I'm going to take it here. Okay, and I'm going to draw on this one. So look, my one's a bit messy. Okay, so likewise here, what do we got? We've got, we're doing the same thing now with the green graph, same process, because essentially the first derivative of the green graph is the second derivative of the purple graph. So again, we're plotting the first derivative, but this time of the green graph. So where are our turning points again? First of all, turning point here, turning point here, turning point here, turning point here. That's this, 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 and this. Okay, and we've got a negative gradient leading up to this turning point here. So we definitely have a 0 at this point here. We have a negative gradient leading up to that. So we've got negative, and then we've got positive, the green graph between here and here. So we've got negative, we've got positive in between these two, something like that. And then we've got, it changes to negative between the next 2 points between here and here. So somehow we've got to do a negative, and then it goes positive again, and then it goes negative again. So it's going to look something like this. Okay, now again, can we see anywhere which is more steep than other places? Because that's where I fell down last time. So let's see. So let's see that this is more. This is perhaps more steeply negative. This one here is more steeply negative than what is going on this side potentially. Okay, so maybe this goes down further, and even that's maybe more steeply negative than this. So maybe this is like a deeper sort of turn, and the other ones are kind of moderate. And then we've got sort of like this. So something like this, getting sort of steeper in the middle, and then like this. Okay, I think it should just go through like that. And you want to just do like a smoothish curve there, going through each of those things. Okay, now there's a point of inflection at these points as well. Not necessarily a point of inflection. The point of inflection would be down there, for example, I think. Okay, so let's have a look at that, and let's see what they've drawn. And there we go, they've drawn similarly something like this, and you can see they've got a deeper turn in the middle than the two to either side of that. Okay, and I'd actually argue that this is going to be less negative than this point down here, and they have drawn that more negative, in fact. So actually, I think there's potentially something wrong with their graph. Now, again, we don't really know the scale of this. We don't know the y-axis scale, so we can't really put on that y-axis scale unless we've actually found out a gradient at a particular point. Okay, so there we go. That's that graph. Let's just zoom back out again. That leads to exercise 4P. And then for the next one, again, another investigation, which I'm not going to have a look at. Obviously, you're welcome to look at that. And example 33 now takes us through to the next exercise, 4Q. So again, we've got to think about how to draw these ones here. And this one is talking about, I have to actually make this one a little bit smaller. This is talking about, well, let's look at it first of all. It says, here's the graph for the function. And it says, from this graph, indicate the x coordinate of any turning points where f has turning points. Okay, so we're given f dash of x, and we need to think about where the turning points are for f. So it's going backwards. Now, remember from last time round, where the turning points are on f is going to give us f dash of x is equal to 0, a gradient of 0. So where the zeros are on f dash of x are going to tell us where our turning points are for the original function. Now, it might be useful to be able to try and go backwards here. So what I'm going to do is just again zoom into this one, steal this one here. It might be useful to try and think about drawing the graph going backwards, but we have a bit of a problem here in that we don't really know whether or not when we go backwards, whether we've got on the original function, whether we've got blah, 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 something plus c. Because if we've only got f dash of x, that c has disappeared. So we don't really know. We don't really know where the graph is going to plot. It could be plotting up here, or it could be plotting down there, because we don't know about this plus c, and we can't know about it because it's lost information when we differentiate. Now, when we integrate, which is going backwards, we will put in this extra plus c there. That is the sort of constant of integration. Okay, so let's just try and figure out where it might go, though. So if we have a 0 on f dash of x, that's a turning point. So somehow we have a turning point. We have a turning point there. We have a turning point there, there, and at this point. So there's 4 turning points in this graph. Okay, now for those 4 turning points, and we don't know where they are on the y scale, for those 4 turning points, we need to think about whether they're maximum or minimum. Well, for this one, we can see that the gradient is negative all the way up to this point here. So we've got a gradient which is negative. Oh, sorry, up until this point here. We have a gradient which is negative. That's saying gradient is negative because we're below the axis. Gradient is negative, we're below the axis. So up until this point here, we have a negative gradient. Negative gradient means we're coming down like this. That would be positive gradient. Now, anything between these 2 turning points is positive because we're above the axis. All of these answers are positive. That means we have a positive gradient between these 2 turning points. Now, that means, this point must be higher up here. Now, between these 2 turning points, between these 2 lines here, essentially, we've got negative answers. So negative answers mean, again, just thinking that this turning point is somewhere here, and then after that point, we're going to get, go kind of up like this, and then it's going to go down again. It's going to be negative. So then we're going to hit this point, okay, turning point there, and then again, we're going to get a positive gradient. So positive gradient, the last turning point, somewhere like this, something like that. Okay. Right. Okay. So there we go. That's our graph. Looks to me like we've got 1, 2, 3, 4 turns there. So this is a quintic. And you can see that the dy dx there, or f dash of x, the function which is drawn, is a quartic. And we're expecting it to have degree 1 less than the function, which is the original function. Okay. Anyway, we've drawn that one out. And that's just a possible version. So of course that whole thing could be up or down, or scaled up or down as well. So it could be down like that instead. We don't know where this function is because we don't know if there was a plus c on the end. Okay, so let's look back at the question. So if we can answer some of these questions now. So it says, there's the function. Let's just steal this thing here. Okay, and so from the graph, indicate the x-coordinate points, x-coordinates of any points where f has turning points. Well, we can see it's here, 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 here. Okay, so x-coordinate points, so that's going to give us -1, 0, 1, and 2. Okay. By the way, a graph for that could be, if we wanted to create that quartic for this graph here, we could see that that could be x plus 1, x, x minus 1, and x plus 2. Maybe that's how they created this f dash of x graph in the first place, or some scaled up version of that. So that could be your function for the quartic, because it's got those 4 roots. Okay, so then it says after that, of course, the intervals for where f is increasing. Okay, well, we've essentially just done that. Where is f increasing? Well, f is increasing when the gradient is positive. So we need to think, when is f increasing? That's when f dash of x is greater than 0. So that's between these two and between these two here. So that's between -1 and 0, and between 1 and 2. Okay, so there's where it's increasing. Where's it decreasing? Well, in the other areas. So here and between here and here. So you can write down those inequalities as well. Okay, the x-coordinate of the points of inflection of f. Okay, so points of inflection of f, let's just think of that. That's going to be when f dash dash of x is equal to 0. So now we need to think about differentiating this graph here. Well, where does this graph, the f dash of x, have turning points? Well, that's when we're going to have f dash of x is equal to 0. Okay, so this is f dash of x. We need to differentiate this again and set it equal to 0. But if we differentiate it again and set it equal to 0, we'll find the turning points. So there we go. There are going to be the points of inflection. So the x-coordinate points of inflection are going to be essentially differentiate again, set equal to 0. That's this thing here. Set equal to 0, that's a gradient of 0 on f dash of x. And so that's going to be at this x-coordinate point, this x-coordinate point, and the one here, 1.62, I think it is. Okay, so there's that sorted out. The intervals, let's go back a little bit here. Right, okay, the intervals where f is concave upwards and f is concave downwards. Now, this is where a sketch of f is going to be useful, but where it's concave upwards, well, again, I would come up with a sketch here, I think. So remember we had turning point, turning point, turning point, turning point. And remember we had negative going into this, then positive, then negative, then positive, then negative gradient again. So actually turning points have to be something like this. Okay, now where is this concave upwards? Well, it's concave upwards all the way until 0. So it's concave upwards when x is less than 0, and it's concave, sorry, that's not correct. It's concave upwards up until this point of inflection here. Or point of inflection, this point here, that's what they were leading us to before. So actually it's up until this point here, and then we have this point of inflection on our graph. Okay, so we've got to think concave upwards, where are we getting f dash dash of x is greater than 0. Now we've found that where it's equal to 0. So it's equal to 0 at this point here. So let's just say f color. So we've got f dash dash of x equal to 0 at this point, and this point. So now we just need to think, where are we greater than 0? Where is it concave upwards? Well, that's all up until here. And so what we're thinking about there really is what's the gradient of the gradient function. So what the derivative, so we're thinking about when the derivative of f dash of x, second derivative, is positive. So when are we getting positive gradients? We're getting positive gradients all the way up until this turning point. So this is going to be our case. Just highlight this. So this is all the way until here. So that's until this, up until this, point of inflection. And then it's also concave upwards between this point of inflection, which is here. Okay, and so there's the other point of inflection on there. Okay, and so we're getting between here and here on the sort of grey graph which I'm drawing is also going to be concave upwards. In other words, in this section here. Now, obviously, the other sections are going to be concave downwards. Now, that's all a little bit messy, but once we've done f dash dash of x is equal to 0, in other words, here, here, and here, then either side of those we need to just think about whether or not we're greater than 0 or less than 0. And that depends on thinking about doing on our f dash of x, when do we have a positive gradient? That's essentially what we're asking when we're asking for this. We're saying when is there a positive gradient of f dash of x? Now, I just wanted to check how the book has done this as well, and you can see that the book really hasn't made too much of this. It's just said f is concave upwards when f dash dash of x is greater than 0, and that's up until our turning point on the graph which they've given us here. So when x is up until minus 0.62, and then when is it concave upwards? It's also concave upwards when we have another positive gradient section on f dash of x, and that's between 0.5 and 1.62. And you can see that that's what they put in answer D there. Okay, so for the last part of this, it says sketch a possible graph of f using your answers from A, B, and C. Now, I did that at the start, and their one is looking quite different. But the truth is here, when we draw the possible graph, so they've put the green graph on there as the original graph, I think. Yeah. Okay, and they've put on this purple graph here to say, well, that's a possible graph. Now, they've said that that potentially goes through 0, 0. Now, I've copied that one across onto here. So again, green graph is the original graph. So that's green graph is f dash of x. And then the purple graph here is supposedly f of x. Now, they've done similarly to what I've done. I've said, well, at all of our zeros here, we've got turning points. And so there's a turning point there, there's a turning point there, and there's a turning point there. Now, perhaps they've done a sort of scale of the function better than I've done, but you can definitely see that we have to have a negative gradient up until the first point, then a positive gradient, then a negative gradient, then a positive gradient, then a negative gradient. We can see that from whether or not the green graph is below the axis or above the axis. That tells us about the nature of the gradient. Now, you can see that it's gone through this point here. I think you can't say that it goes through that point, though, because, of course, when you differentiate this, you lose the plus c. So they've put it just going through 0, in other words, assuming that there isn't a c, but it's quite possible that it goes through this point up here, and the whole of this graph goes up by 4, because we don't know if there was a plus 4 on the original function. So it's something like this. I think it's really hard to tell, in fact, whether or not these points, this point is above this point or not. I don't know that I could tell that from the original graph. So, I mean, I think some sort of sketch doing this is sufficient there. Okay, and then you could potentially try and put in values to f of x if you can find a function for f of x But that requires us to know about integration, so to know to go backwards, and we don't know about that just yet. Okay, well, I'm going to stop there. And there's another investigation there, so you can have a look at that one too. And then there's 4Q, and there's 2 questions there, but different sections of those questions. And then after that, we're going on to applications of differential calculus, talking about optimization to start off with. So a practical use for differentiation, and I look forward to doing that one, and hopefully I'll see you for the next video as well. Okay, well, good luck with the exercise, and see you later.